identical atoms, that would be considered to be non-polar. And again, this is probably a concept that you might have encountered in your first year of chemistry, but when it's non-polar, the bonding electrons are shared equally between the two partners. And that would make sense. If it's carbon and carbon, or hydrogen and hydrogen, it's going to be fair. They're going to want the electrons equally. There's not going to be one preference for one atom over the other. But all other bonds, and we are going to, and I should probably just build this into the handout. All other bonds are polar, except for one scenario. Carbon and hydrogen is the one exception to that. That's the one case where we have a bond between two different atoms that we are still going to consider to be non-polar. So somewhere in there, if you want to write in that carbon to hydrogen is an exception to this. And for the future, I think I need to make a note for myself to maybe change that effect. Do that right now. That will force my hand to remember to do that. And what we mean by that is the electrons, if we say the bond is polar, in other words, the electrons are preferring to be closer to one of the two atoms. And the way what happens there is we have a shift in the electrons where they're at in the molecule, and it can cause not ions, but we get partial charges. So we start to see within the molecule that some atoms will start to have a partial positive charge, some atoms will start to have a partial negative charge. And that's what's really going to start to influence how we do reactions in organic chemistry, because we'll have these slight positive and negatives that on different molecules that may want to interact with each other, and that's going to kind of get things going so that we can have chemical reactions. And we're a little ways off from that. We're going to do a lot of the structural stuff first, but that's going to kind of lead us to that. And what determines this concept of a polar bond or bond polarity is the concept of electronegativity. And again, probably something that came up at some point during general chemistry. A real sort of generic definition for electronegativity, a lust or desire for electrons. And I fixed for the new edition, if you look at McMurray page 34, I believe it is now, figure 2.2, there are numerical values for all of the different atoms and their electronegativities. This is one thing I'm not going to ask you to memorize. That would be a lot of different numbers, and you can look these up in tables, it's easy to find them. We're not going to memorize all of those electronegativities. There are a couple of things that you can use to kind of do a handy guide for this. One is if you're looking at the periodic table, electronegativity tends to go up as you go up columns in the periodic table. So the top of the periodic table the atoms tend to be more electronegative than the ones at the bottom. And it also tends to increase as you go across the periodic table. So if we throw the noble gases out, like helium, neon, and those guys in the last column of the table, they don't typically interact with other elements and other atoms. So ignore the noble gases. The upper right corner, the most electronegative atom is fluorine. The worst would be somewhere down in the lower left, maybe cesium or rubidium, somewhere in there. Francium is fairly rare, so we'll ignore that one. And think about those elements in the first column. They like to give electrons away and make a +1 ion, A+, K+. So that's kind of they're so low in electronegativity that the electrons just get pulled away from them. Just like in column 2, Mg+2, Ca+2. So if we think about the nonmetals in the upper right corner, we have varying degrees of electronegativity. And Falkland-Birch, which again, here's our crude attempt at some sort of acronym that chemists would come up to keep track of this. FOCLN, fluorine, oxygen, chlorine, nitrogen, bromine, carbon, hydrogen. That's kind of how you can keep track of the electronegativity order for the elements that are common to organic chemistry. So as you see on that little diagram there, fluorine the most electronegative, hydrogen would be the least electronegative. Notice carbon and hydrogen are right next to each other there. So they are, while they are different, carbon, if we looked at the table in McMurray, the electronegativity of carbon is slightly greater than hydrogen, but not great enough that we really see the electrons shift that much towards the carbon and away from the hydrogen. That's why CH is still considered to be nonpolar, because it's pretty close. It's a difference, but not a big difference. The rest of the differences in electronegativity, H to Cl, or H to Br, carbon to bromine, carbon to any of the others, are big enough that we consider that the bond would be affected a little bit and would be what we call polar. Questions so far? Anything that's not making sense or anything? Okay. In a polar covalent bond, the atom with the higher electronegativity will be partially negative. So now we're underneath that diagram there. And we write a little delta sign. We're using the lowercase delta. You might be more familiar with the uppercase delta, which is a triangle that we use for things like in thermodynamics, like delta H, delta G, delta S, that you might have learned. So that's a capital delta sign, sometimes used in Greek letters for organizations and things like that. The lower delta is a little bit like a funky looking D, like a regular lowercase d, but it's got that little tail on it. But a delta minus for a more electronegative atom, a delta positive for a less electronegative atom. And one example there of a polar bond would be HF. So if we just imagine making that bond for a second, and I think we could do it like that. I just gave you the formula, I didn't give you the actual bond. So there's the molecule HF. We have a covalent bond with a dashed line between fluorine and hydrogen. And if we want to get really technical, there would be these pairs of electrons, of course, on fluorine. So everybody's happy. 2, 4, 6, 2 electrons here. That's 8 electrons around fluorine, 2 electrons around hydrogen. So they're both achieving their full number of electrons that they're shooting for. So there's our covalent bond that we get by sharing those electrons. But because of Falkland-Birch, we know fluorine wants these 2 electrons a little bit more than the H does. So we imagine the fluorine having a partial minus, and over here by the hydrogen we could write a partial or delta plus. So that's one way that we could show the bond polarity, is by putting these partial plus and minus signs next to the various atoms that are considered to be affected by the polar bond. Yes, Sarah?
Is the fluorine more negative, is it 90-10 kind of thing? Or is it supposed to be equal?
Well, that's where those numerical values come in. There's a bigger discrepancy between F and H, for example, than there would be, say, if fluorine were making a bond to nitrogen. If you think about Falkland-Birch there. Fluorine-nitrogen would be polar as well, but the electronegativity difference isn't quite as big there, so the electron, it's kind of like a tug of war. So if you imagine, you've got 2 teams with a tug of war and you have the flag in the middle. If you have one team, like in this case fluorine, that's really strong, and one team that's really weak, we're approaching ionic at this point. We're not quite there, but we won't ever quantify it specifically like you were just asking, like 90-10 or something like that. But we would imagine that the polarity in HF would be greater than it would be for, say, HN, or something like that. Or FN would be not as polar as FH, that type of thing. But we're not going to actually quantify that. But yeah, so, and then the extreme again would be if you got something that was so much greater than one versus the other that's when you get the ionic bond. So if you had F and Na, they wouldn't form a covalent bond anymore because the fluorine would just take the electrons and the sodium would be attracting it so weakly that it would just give out the electrons. So that's kind of the extreme. So this is one way that we can represent that that bond is polar, a partial plus and a partial minus. The other way that we sometimes do this is by showing a dipole. And a dipole is an arrow that points in the direction that the electrons are moving. So it's kind of like your play-by-play for the tug of war. So we would, in this particular case, maybe draw an arrow just moving in the direction of the fluorine. That's another way that we could show that that's a polar bond. So either one of those is a way of doing that, whether it's the arrow or whether it's the delta plus and the delta minus. Yeah, question?
I was going to say, if you like draw the arrow, would you not still draw the electrons on the
These?
Yeah.
Yeah, those lone pairs are still there. We're really talking about what's happening to the electrons in the dashed lines, the idea that those are moving closer to the fluorine. So instead of these electrons being dead center here, right in between the H and the F, they're drifting this way a little bit towards the fluorine. So the arrow tells us that, or the delta minus on this side and the delta plus on the other side would tell us that as well. Other questions? Okay, so we have these bonds that are directly polar as a result of one atom being more electronegative than the other. We can also have something that we refer to as the inductive effect. And this is sort of a response to a polar bond somewhere in your molecule. And as the definition says there, the inductive effect is the shifting of electrons through sigma bonds, those simple bonds that we have in molecules, in response to the electronegativity of nearby atoms. And the way that we can sort of represent this is if we imagine let's imagine this molecule here. And next Wednesday, let's, for example, say we had this molecule on our quiz next Wednesday, and it said identify polar bonds. And we look at that molecule and we see, and this is where sometimes I might still give you an expanded structure. I told you we were going to phase those out, but sometimes here when we're trying to identify polarity, we might still, do the expanded structure so that we can really see the individual bonds that could be polar or non-polar. Eventually we'll get rid of it completely. And we look at this structure and we say, well, carbon to carbon, that's non-polar, it's the same atom. Carbon to hydrogen, Falkland-Birch, carbon's a little bit more electronegative, but he told me to add in at the top of that handout and say, okay, C and H are close enough that that's okay. So we find one scenario here where we have a polar bond, which is what?
Cl.
C to Cl. And I'll take a volunteer if I can get one. Which way should the arrow go if we were doing a dipole? Karen?
Towards the Cl.
Towards the Cl. Yeah, Falkland-Birch, Cl wins in that. So the arrow is going towards the chlorine, away from the carbon. The other thing that we could do is we could say, all right, the carbon is slightly positive, the chlorine is slightly negative. There's a consequence to that to some degree. If this carbon becomes slightly positive, it's now, when it's attached to this carbon, not necessarily completely equal to the other carbon that it's attached to. This carbon has a little bit more electron density around it, if you will, compared to this carbon, because this one has lost a little bit of the electrons in that octet to the chlorine. So the carbon in the middle is feeling slightly positive. The inductive effect would be that the electrons in these two carbon-carbon bonds would shift slightly in the direction of this carbon here to try to help it out. It's kind of like if you have a neighbor in need. You may try to do something to help that neighbor out a little bit. If you know that somebody, your neighbor, they had a death in the family or something, they've got a lot going on in their life because of that, things like that. You might cook a meal and take it over to their house, and say, here, we made this so you don't have to cook dinner tonight. You don't have to think and worry about doing that, because you got so many other things. You got people coming in from out of town, all of this kind of stuff. So you do something to help them out, or whatever it is. So it's a response to this polar bond. We don't necessarily call it a dipole, but it is a little bit of a shifting of electrons. We might draw a kind of little tiny arrow to represent that inductive effect and indicate that the electrons are flowing that way. But it's not quite the same thing as a dipole, but it is a shifting of electrons in response to that polar bond. So we will encounter this type of effect as we go throughout organic chemistry. So mentioning it now, we don't necessarily call it a polar bond, but it is a little bit of a shifting of electrons in response to that polar bond. I saw a hand or two. Good? Okay. Anybody else? Okay. All right, so that's our first concept here in chapter 2, is the idea of the polar bond and also potentially the inductive effect. Now, we can take that a step further and not only think about a polar bond in a molecule, but think about whether a molecule itself, in the big picture, whether the molecule is either polar or nonpolar. And there's some interesting scenarios that can come up with this. The way that we go about determining this, as you can see, there are a few rules there for that. We draw the Lewis structure, or line bond structure really when it's all said and done, where we put in the lines for the pairs of electrons to make bonds. And we apply VSEPR, which I loosely mentioned when I was talking about our desire for shortcuts in names and structures and things like that when we were doing that the other day. Valence shell electron pair repulsion. Again, the idea that groups of electrons around your atoms are going to want to be as far apart from each other as possible. So CH4 is tetrahedral, not a flat square or diamond-shaped molecule, and things like that. So we apply VSEPR to redraw the molecule in the proper three-dimensional shape. That's step 1. Oh.
Okay.
Oh, sure. Okay. Step 2. Draw a dipole for each bond in the molecule. So any places where we have polar bonds, we draw an arrow, and then we add them up. And that's kind of in quotes there, but we take the individual bond dipoles and we try to check and see if there's a net dipole, and we would draw that in. And as bullet point number 4 says there, sometimes the bond dipoles will cancel each other out. And then even though the molecule might have polar bonds, they cancel each other out and there's no overall polarity to the molecule. There are polar bonds, but it's not a polar molecule. And the thing that I would add to that, for the bond dipoles to cancel each other out, they have to be equal and in opposite directions. Equal and in opposite directions. And one place that we can easily go to think about that would be if we look at the clock. Maybe doing that thinking, when the heck is this class going to be over? I can get out of here and step out and listen to all this organic chemistry junk. But if we actually look at the clock for real right now, one of the hands is pointing towards the 8. And let's see, we'll pretend we're back in elementary school. The big hand is the one that's pointing towards the 8. What would be the opposite of 8? 2. So if instead of being 8 and the other one pointing more towards the 4 and the 5, if that other hand was pointing towards the 2, Those would be in opposite directions. Now on the clock, if we think of the arrow representing the size of the dipole, the little hand and the big hand would not cancel each other out. So in that particular case, there would be even though they're in opposite directions, there's more of a pull towards 8 o'clock than there is towards 2 o'clock. But if the two hands on the clock were the same size, and you had one going towards 2 o'clock and one going towards 8 o'clock, or use 12 and 6 if you like, since they're straight up and down, and the amount or size of the dipoles were identical, they'd cancel out. So if you had an arrow pulling from the center of the clock towards the 12, and an arrow pulling from the center of the clock towards the 6, that was equal in size, they would cancel out. And there would be no net dipole for that scenario. That's what we're talking about here. Yes?
So how would you know, like, because you say they have to be equal, like, is there a numerical value, or are we, like,
Well,
what are we looking for?
we could calculate the numerical values, but a lot of times we'll know because they won't necessarily be the same type of dipole that we're looking at. So it's probably easiest if we do an example or two. So let's start with one that's not too bad here. Let's do CH3Cl. All right, well, I know that carbon is going to be in the center. It's the only one that can make multiple bonds. Chlorine and hydrogen can't. And when I have 4 bonds around carbon, I make a tetrahedron. So how I kind of represent that is I'll have a bond or 2 actually that are planar within the board. And then the other 2 parts of the tetrahedron, one of them would point back inside the board, and the other would point forward, coming out towards me. Well, it's kind of hard to do that. You know, I could put the marker here to kind of represent the thing coming out towards me, but I can't drill a hole into the board and put the other thing back in there. Or if I did, they'd be pretty mad at me, I guess. So we won't do that. So what we do is we typically draw a wedged line to mean that whatever's being represented here is coming towards us. See how it starts small and gets kind of bigger. And the thing going away from us, we kind of use a dotted line, meaning that it's pointing back away from us. So there's how we represent with VSEPR the sp3 or tetrahedral geometry. And now we have to fill in 3 H's and a Cl. And where we put the Cl is really up to us. Doesn't really matter. For ease of doing this, I'm going to put the H's here at the base of the tetrahedron, and I'm going to put the chlorine up here at the top. And now, so that was step 1. I came up with the Lewis structure, I applied the SEPR, VSEPR, and I got the shape of the molecule. Now I am going to draw a dipole for each bond. Well, CH doesn't have a dipole. The only dipole I have, just like we talked about here, is C to Cl. And now I'm going to add those up. Well, it's easy when you only have one thing to add it up. Not too hard. You know, if you guys were the only class I had, and I said, how many students do I have? It'd be whatever number this is. I have 2, so I have to add 2 numbers together. But in this case, I only have one thing. And if I have only one thing, it's kind of hard to cancel it out as well. If there's one hand on the clock, there's not another hand there to point in the other direction. So in this particular case, the overall dipole for the molecule would be pointing up towards the chlorine. This is a polar molecule. The electrons in CH3Cl are shifting a little bit in the direction of the chlorine and away from this side of the molecule. So this side of the molecule is slightly negative. This side of the molecule towards the bottom, in this case, is slightly positive. Questions about that? Yeah.
So confirming it's polar because it's shifting in the direction of the chlorine, which has a polar bond between C and C.
Yeah, and it could be the other way too. If carbon was more electronegative than chlorine, and the arrow was going from the Cl to the C, that would still be a polar bond that would not be canceled out. So In that case, we would say but for the overall molecule, then the arrow would go this way towards the carbon, just like in the bond.
So it doesn't have anything to do with the polar, like, so that doesn't.
It's the overall dipole for the molecule would be in the direction of whatever the more electronegative thing tends to be. So in this case, since chlorine is more electronegative and that bond is more polar, that's the direction the dipole goes. And we're going to do a couple of more examples yet that will help to hopefully reinforce this a little bit. But first, another question.
With the one that you drew earlier,
Yeah.
how would you draw that with Vesper? It's like, how are we supposed to know with like multiple?
It gets a little tricky, and I didn't bring my models today, but remember we had this sort of zigzag shape for the 3 carbons? So you'd have kind of a tetrahedral thing around each carbon. In this case, again, we only have one polar bond, so we're kind of fortunate there that we know it's going to be that one bond is going to be where the polarity is. So we might have to, with that, just kind of, we might draw the tetrahedron around this carbon and not worry about the tetrahedron around the 2 carbons that are nonpolar, because we know they don't have any effect because they're CH bonds. So that would be the other thing, is we might not have to think about the shape of the entire molecule. In this case, just the carbon that has the polarity. So that would be a way around it too. And we can sometimes fudge it a little bit with the Vesper as well, if we're pretty certain that it's not going to cancel out. So that sometimes is where we can maybe not worry quite as much about the shape if we know for certain that there's not going to be a canceling. But let's try another one. Let's take this molecule here where we have a carbon-carbon double bond. We have an H, we have a Cl, we have an H. I'll put the H up here, and I'll put the Cl up there. Now in this molecule, carbon to carbon, even though it's a double bond, it's still equal. They're both going to share the electrons equally. Carbon to H, close enough. Carbon to chlorine is a dipole. Carbon to chlorine, that's also a dipole. They don't cancel each other out. They're not pointing fully in opposite directions. This and this are not opposites. This and this would be opposites. 12 and 6 are opposites. 8 and 4 are not opposites on the clock. 8 and 2 are opposites. 4 and 10 are opposites. So in this particular case, and you could apply physics and adding vectors. Some of you may have seen that in physics already. Some of you might not have taken physics yet. So if you haven't, that's okay. But if we think about the overall direction that these 2 are heading, they kind of add up to point towards the bottom of the molecule as opposed to the top. So this molecule has polar bonds and they don't cancel out. And the main conclusion, even more so than just the idea of where the arrow for the dipole in the molecule is pointing, is that this molecule would be, in fact, polar. Yes?
How would we know to draw it like that instead of putting the Cl where one of the H's is, and then they would cancel out?
Well, you, in some cases, it might be a case where if all you had was the formula, if I simply said you have the molecule C2H2Cl2, you wouldn't necessarily know to draw it like this versus this. And what you were getting at, and this is where I was going next, so I'm going to just continue for a second. Carbon to chlorine, those 2 are equal because chlorine pulls on carbon just as much as the other chlorine pulls on the carbon. So they're pulling equally, yet in opposite directions. So they cancel. They are equal and opposite. So that particular example would be nonpolar for the molecule. Now, there are two parts to this. I'll come back to you in just 1 second, in case, especially if I don't answer this. Two parts to this. Are there polar bonds in that molecule? Yes, absolutely. Is the molecule nonpolar or polar? That's a separate question, and in this case, the answer would be nonpolar. So there are two things that we can ask ourselves. Are there polar bonds? And then also, is the molecule overall polar or nonpolar? Now, getting back to answer first your question, Cameron, and then Mel, right? Okay. All right. So if and if I don't ask, if I answer yours, great. If not, we'll come back to it. But to get your question first, if we simply gave you the formula C2H2Cl2 for a molecule, there's really no way that you would know to draw that or that. You could draw either one. Both are representations of that formula. They're what we call isomers, and we'll get into isomers probably next week sometime, hopefully, maybe next Wednesday. They're molecules that have the same formula, but they're a different way of drawing things. Kind of like if we rearrange the seating in the room. You know, we have all of the students here, you know, all of you guys are in here, and you sit in a certain way, but if we said, all right, everybody get up and move to a different seat, you'd all still be in the room, it would still be the same class, the same students, but you'd be in different places. That's kind of like what we did here. We took the same molecule, but we just put one of the chlorines in a new spot. So there's no way to really tell that just from the formula. So in a case like that, if I were going to ask a question like for that molecule, I probably wouldn't just give you the formula. I would give you either that specific structure or this specific structure so that you can answer the question. In the case of CH3Cl, I could get away with just giving you the formula and asking you to go through the whole thing. So even though we have rule number 1, there will be a lot of times when I provide you with the structure from rule number 1 and just ask you to do rules 2, 3, and 4. So I'm going to take some of the work out of your hands and make it a little bit easier by providing you with the structure in a lot of cases. All right, did I?
That was it.
Oh, perfect, okay. All right, so there are 2 examples. What if we took this same molecule and did that? Polar or nonpolar?
Polar.
Okay, anybody for nonpolar? I haven't heard a lot of polars dominating the voices there, but anybody want to go with nonpolar? We had elections yesterday in some towns, so we'll take a vote. Okay, nobody for nonpolar? All right, well, it is in fact polar. The polars have it. Carbon to chlorine is a dipole. Carbon to fluorine is a dipole. They are pointing in opposite directions, but they're not equal. The F pulls on the carbon a little harder than the chlorine does, so there's a net effect. Pretty weak probably, but nevertheless we could write an arrow for the molecule going in that direction, and it would be polar. One more for good measure. Carbon dioxide, CO2. Polar or nonpolar?
Equal.
I hear a nonpolar.
Non.
I hear some nons. Any polars?
I want to say yes.
Okay. Well, go ahead then. All right, so carbon to oxygen. Don't be afraid to if you want to. Carbon to oxygen is a polar bond. So is carbon to oxygen. But because the carbon is attached to only 2 things, the 2 oxygens are in opposite directions, 180 degrees apart. So as much as you want to say yes, in this case they do cancel each other out. And CO2 is a nonpolar molecule as well. And it's actually been used as a, we hear sometimes bad things about CO2, and the production of CO2, but in some cases, CO2 has actually been used for quote-unquote green dry cleaning processes, because a lot of the solvents that they use for dry cleaning are chloro and fluorocarbons and things like that. They tend to be fairly toxic. So not just maybe not CH3Cl, but CCl4 or CH2Cl2 and some other chlorinated and fluorinated compounds that tend to be fairly on the toxic side. They're not really great for the environment sometimes. And CO2 is nonpolar, which means that other nonpolar things like dirt and grease and oil and things like that could dissolve in it. So there have been some people that actually developed, if you heat CO2 to a high enough temperature and put it under enough pressure, it becomes what we call supercritical, or almost liquid-like. And then if you had clothes in there and were kind of agitating, the dirt and other stuff that would be on those clothes would come off of the fabric and dissolve in the CO2, and then you can pull that, you can reduce the pressure, convert the CO2 back to a straight gas, the dirt and stuff would fall away, and you'd have a nice clean garment that you could then dry clean, with more environmentally friendly chemicals as opposed to some of these fluorocarbons. So there was some work with that type of process. I don't know how well it's really caught on. It's a little bit on the expensive side, I think, but it essentially the concept took advantage of CO2 being nonpolar. Yes?
Why isn't CO2 bent like H2O?
Why isn't CO2 bent like H2O? Because this carbon has only 2 groups of electrons around it. And anytime, so that's kind of like and 2 atoms on either side of it. So it's kind of like when you have a carbon something triple bond, and you have the other atom on the other side. So it's a 180-degree angle because you're trying to separate this double bond away from this double bond, so they end up opposite of each other. Yeah. Because we only have those 2 sets of electrons and 2 atoms that we are bonding to the carbon. So the easiest way to separate them in this case, what we don't have on the carbon is unpaired electrons that we have to account for to make it tetrahedral. When it's H2O, the O has these extra pairs of electrons that have to get away from everything else, and that's why it gets that bent shape. Yeah.
So, does that mean that CO2 doesn't interact with water?
Yeah, that would it would not necessarily interact with water because they're CO2 is polar or non-polar and water is polar. So supercritical CO2, if it were kind of in a liquid-like state, would kind of form a separate phase with water, and you'd have 2 layers. Yeah,
Like oil?
yeah, kind of like oil and water. Yeah. All right. Any other questions about the concept of polar bonds, polar molecules? All right, then if we go to the back side of this handout that we're working on here, what we're going to see is another concept that sometimes happens where we do occasionally in organic chemistry take the polar bond to the extreme of giving the electrons to one atom or another, and we get an ion. And we develop on a particular atom what we call a formal charge. And a formal charge typically happens when we have an atom doing something that we're not expecting it to do. It either has too many bonds or too few bonds. Or you could say too many electrons or too few electrons. And you see some different scenarios that are given in that table for carbon, nitrogen, oxygen, sulfur, phosphorus, etc. And there's a formula for how we can figure out what the formal charge on a particular atom might be. And we'll go through that in just a second. Clear a little space here. The way that we can calculate a formal charge, and again, this may be something that sounds at least vaguely familiar. It's the number of valence electrons that the atom typically has when it's by itself. Not atoms. I was saying atoms. And there we go. Number of valence electrons. And there are different ways of doing this. The one that's a little simpler to worry about is if we subtract the number of bonds that the atom is making. And then we're going to do one more set of subtraction. So we're going to subtract the number of bonds. We're going to subtract also the number of non-bonding electrons. And just as a reminder, we can use E minus as the shorthand for electron. So instead of writing out electron, I'll start to use that a little bit more frequently. That formula will tell us the charge or formal charge on any molecule. And if you look in the very first column there for carbon, that particular carbon has 3 bonds. You look at it, you see the 3 dashed lines coming away from the carbon, and then they've written in already a positive charge there. But let's say that positive wasn't there, and you just looked at that structure, and you saw the 3 lines coming off of it, and you said, well, that doesn't look right. Day 1, and every day since then, he's been going on and on and on and on. Carbon makes 4 bonds, carbon makes 4 bonds. I only see 3 bonds. What gives? Well, something's not quite right there. Carbon gave away something, it looks like. So we calculate this. And in this particular case, we can go pretty much right down that column, the way they provided it for us. 4 valence electrons, because carbon's in column 4, minus 3 bonds. And if you look at that structure, again, ignore the positive charge for a second. Do you see any dots by the carbon? No. So there are no non-bonding electrons. 4 minus 3 minus 0. That's easy math. That's plus 1. There's a positive formal charge on that carbon, or what we call a carbocation. Yes, ma'am?
Sorry, how do we know that they're not assuming that we're assuming that there's lone pairs there?
Because we will make every effort normally to draw in lone pairs, and indicate that we don't normally expect carbon to have lone pairs. So if carbon did have lone pairs, we draw them in. If you don't see any lone pairs, you would assume that they should not be there.
But even for like oxygen, so.
Oxygen, we would normally assume 2 lone pairs. So if we saw more or less, then we know something's up. So
Okay.
if we're doing a formal charge question, we'll usually make sure that we draw in, however many are supposed to be there.
Okay.
So if you look at the one to the right, carbon has 3 bonds, but now it has a pair of electrons. There are 2 dots there. That also doesn't seem quite right to us. We're like, carbon shouldn't have dots, it should have another line. It should have 4 lines. But it's got 3 lines and a dot. So we do the math on that. 4 minus 3, 1. Now here's where the table kind of fails us a little bit, because that next row in the table is not the total number of electrons, it's the number of lone pairs. There's 1 pair of electrons, but how many are there in a pair? 2. So 1 minus 2 would be minus 1. There's our formal charge. So what you need to do, if you wanted to simply subtract going down any of those columns, you'd need to multiply that 3rd row by 2. Now the first column didn't matter because 0 times 2 is still 0. If you don't have any electrons, you don't have any pairs. But in the second case, 1 pair is actually 2 non-bonding electrons. So it's 4 minus 3 minus 2, not 4 minus 3 minus 1. And you see some other scenarios there. Again, nitrogen, oxygen, etc. If you think about, let's just do one here that we sometimes see. Occasionally, even in general chemistry. The hydroxide ion, HO. Now we know that there's something more to that probably because we've done enough in general chemistry. that we're familiar with that. But we see HO and we look at it and we say, okay, hydrogen normally makes one bond. If we wanted to calculate the formal charge on that hydrogen, we could. How many valence electrons does it have?
8,
Hydrogen normally has
1.
just one. Now it's got two around it, but when it's just the atom, hydrogen atom has one valence electron. How many bonds is it making?
1.
1 minus 1 is 0. I don't see any dots around the hydrogen, so 0 minus 0. No charge on the hydrogen, just as we would expect. It's making the one bond that hydrogen typically makes. That looks normal. But oxygen, we're like, wait a minute. H2O, that's water. That's a normal compound. I only have one H. Something doesn't seem right. There should be something else attached to the oxygen. So now we say, okay, well, let's see. 6 valence electrons minus 1 bond. That would be 5. And 1, 2, 3, 4, 5, 6 dots comes out to be minus 1. That's why we put that minus by the O, and we refer to that as hydroxide. It's not just a neutral OH, it's HO minus. And you can see scenarios for the other atoms there. If oxygen makes 3 bonds, like sometimes happens in a molecule like H3O plus, when we're doing acid-base things and things of that nature. Now the oxygen's making too many bonds, ends up with a positive formal charge. Nitrogen has a similar idea there, and sulfur and phosphorus we can also include in that as well. And let's practice one more of these. I'm going to give you another structure here, and this will lead us into what we're going to do next week. And we do have a little bit more time before we get to our quiz. But this will be a good kind of segue into that. CH3NO2 is the molecule that we're going to do here. This is nitromethane, not that you need to worry about the name right now. And instead of just giving you the formula, I'm going to draw out the structure. And in this particular case, I'm going to give you the expanded structure for nitromethane. There it is. What we want to do here now is we want to take a look at nitromethane and we want to determine, are there any formal charges in that molecule? And if so, what are they? Where are they? So, we could try this for any atom. If we want to practice, we could do this for the carbon. Might not be that interesting, but we could do it. Carbon has 4 valence electrons. How many bonds is the carbon making? 4, so we subtract 4. Do you see any dots that I drew around the carbon? Nope, that's a 0. So 4 minus 0 comes out to a big fat 0. There's no formal charge on that carbon. More often than not, most of the atoms in your molecule will not have a formal charge. It would be a pretty bizarre molecule if almost every atom in the molecule had a charge on it. That would be kind of a pretty strange thing to do. Hydrogen we talked about when we did hydroxide just a minute ago, but I'll do a quick one for, this will work for any one of the 3 hydrogens. For hydrogen, 1 valence electron minus 1 bond minus 0 electrons being shown. Hydrogen also has 0 formal charge. Where do we have a candidate that we might consider a formal charge could be existing here? Okay, nitrogen. Let's test that one out because nitrogen, as we were learning in the last week or so, is in column 5, 5 valence electrons. So we know that for the calculation. So it would mean it would normally make 3 bonds to get to 8. This nitrogen doesn't look like it's doing that. Nitrogen in this case, 5 minus 4. I see 4 lines coming off of the nitrogen in this case, not 3. And do I see any electrons? No. 5 minus 4 minus 0. Hold on to your hats with the math again. Get out the calculators if you want. Just kidding, hopefully that's not necessary. 1. That nitrogen has a +1 charge on it. So when we draw nitromethane, we should really put a plus next to the N. There's a positive charge on that nitrogen. All right, I see some hands.
The double bond is considered 1 bond or 2 bonds?
2 bonds.
Okay,
It's 2 different sets of, that's 2 bonds, yeah.
okay.
Yeah, so the nitrogen in this case is making, because when we said when carbon had a triple bond, it was still making 4 bonds, 3 to 1 carbon and an H or a C or something like that. So it still adds up to the number of bonds, yeah. And
Does it matter where the location of the positive sign is?
no, I put the positive here because I had already drawn this little arrow starting up here, but yeah, I can put the positive here or here or here, yeah. As long as it's in the vicinity of the nitrogen. We don't want it to drift over that it's too close to the carbon. Somebody might think it's the C and not the N, but as long as it's somewhere around the N, that's good. Well, hold on a second. When I wrote the formula for this, it said CH3NO2. It didn't say CH3NO2+, did it? So, anybody else in this atom or in this molecule looking a little funky?
The oxygen
Which one?
with 3 sets of lone pairs.
Okay, yeah, the one on the bottom here with the 3 dots. This oxygen has typically, oxygen always has 6 valence electrons. It's making 1 bond. It's kind of like hydroxide just a minute ago. And I have 3 pairs of electrons, or 6 electrons total. 6 minus 1 is 5, minus 6, minus 1. There is a negative formal charge on the oxygen, that oxygen. If you might say, well, what about the other oxygen? Well, that oxygen is making 2 bonds. It only has 2 pairs of electrons. Check yourself, or check me if you like. Do the formal charge calculation. The other oxygen should turn out to be 0. And this is why also that this molecule is just CH3NO2, because in the molecule we have a minus and a plus formal charge, but they cancel each other out. So overall this molecule is neutral. Just because one or more atoms have formal charges doesn't mean the molecule has to have a charge. In this particular case, they cancel each other out, and it is a neutral molecule. But we do have some places in the molecule where things are, not normal, so to speak, and you've got a plus and a minus charge. Yes?
So the other order would be 6 minus 2 minus 2?
4. 6 minus 2 minus. Remember, it's the total number of electrons, not the number of pairs. So you add up all of the dots. So 6 minus 2 minus 4, that would give you 0. So we can have a molecule like hydroxide where there is just 1 formal charge that essentially makes an ion, and there's nothing to cancel it out. Or like in some of those examples there where you have a carbocation or a carbanion or a nitrogen or oxygen with an overall negative or positive formal charge. Sometimes we can have a molecule where the charges cancel each other out. Now, one thing that you might have been maybe thinking about as you were looking at that and the structure that I drew. You might have looked at that and said, well, why that oxygen for the single bond and that oxygen for the double bond? Why not this? Why not that? Because if you draw that one, remember we came up with a plus charge here and a minus charge here. If you draw this one and calculate formal charges, guess what? There's gonna be a plus on the nitrogen, and there will be a minus on an oxygen, but it's the one up here. So why did I draw this one and not that one? Very simple answer. This is the one I picked. Simple as that. There was nothing that should have made me pick this one over that one. And I just as easily could have done this one. If I had given you that formula, CH3NO2, and told you, okay, you're gonna draw a carbon with 3 hydrogens, there's gonna be a nitrogen, and then the nitrogen is making a double bond to one oxygen, and a single bond to the other oxygen, draw that structure. And it may not have been perfectly split, but half of you might have drawn this, half of you might have drawn this. Both of these Lewis structures, as you might say, are valid representations of this molecule. They're both equally possible, and I gave it away there a little bit. You caught my slip there, I think. These are both what we call resonance structures. They are Lewis structures that represent the same molecule, and they are only different by where the electrons are located. And we can get from one to the other just by shifting around the electrons and moving around the electrons. We are going to spend a decent amount of time going over this on Monday. I think I'm going to stop here so we can get to our quiz, and I can give you at least 15 minutes of class time if you need it. On Monday,